All right, so the topics that we'll cover today, like I said, we'll talk about our 615A data loader SDK. We'll look at the software API, so we'll have some pseudocode and talk through the main kind of flow of an application program and give you the idea of what you get for functions in the software API to that. And then we'll also talk about the configurable parameters of the library, what parameters you can configure in the protocol stack. We'll do the same thing for the target SDK, so that's the LRU side. And then we will also look at our ARINC615 media builder. So if you haven't joined any of the previous webinars, we talked quite a bit in both of those about ARINC615 loadable software parts. That's LSPs, and also media software parts, MSPs. We'll go over some of that content again today, but primarily that part of the presentation will be about our tool, the AIT tool that we provide supporting building 665 media sets. As I just mentioned, we've done a couple of these webinars already. The first one was an overview of the data load protocol. So it was more looking at the messages and the sequencing and the protocol exchanges related to ARINC615A. And then early this year, we did another one covering the secure handling of field loadable software. And this was primarily focused on some of the latest regulations and recommendations for applying and using digital signatures on loadable software parts, specifically digitally signing the ARINC615 LSPs. You can, I have the link here below. Both of those previous webinars are still accessible on our website at the URL below there. You can get a link to the videos and you can view those and listen to them if you missed them, or if you just want to listen to them again. I will also post the recording of this presentation after I'm done today, so that will also be available from the same URL. It'll be on the same page. Look for that in a day or two after we get through this today. All right, so just to kind of present a picture of what we'll be going down into today. So the image in the middle there is a data loader connecting through an Ethernet network to one or more avionics systems. In this case, we're showing the MMRs. The data loader SDK, again, that's the library and the protocol stack that you would use on the data loader side. So to load software from the data loader to the avionics systems. And the ARINC615A target SDK, that is what you would use to embed on your own avionics system, or LRU. And so that goes on the loadable system side, or the loadable avionics system. With our data loader SDK, we provide it in a C API. So we provide access to the data load functions in a C API. Also, we provide a command line. And again, that's the data loader side operations. We currently have that available for Windows and Linux, but we will also do other operating systems on request. Then on the 615A target side, we currently have that SDK available for Windows, Linux, VxWorks. I think we've done a smattering of other real-time operating systems, but also we port to other OSs if you have requirements on request. All right, we'll jump down into the data loader SDK a little bit first here. So kind of a component diagram showing the components of the data loader SDK. So we basically have two libraries, so two shared objects or two static libraries, depending on how we deliver it specifically for your application. If you're on Linux, or they would be different DLLs, two different DLLs on Windows. So we have the TFTP library, and there's a TFTP API to that. Then we have the ARINC615A loader library, which actually uses the TFTP library, and we have a C API to that. So the TFTP library, again, it provides basic, easy C functions for doing things like file puts and file gets. We'll look at some code and a pseudocode of an application to that in a couple slides here. And then the TFTP library goes directly to the sockets, the UDP sockets library that's available on the operating system that we port that to and deliver it for. So it goes directly down to the sockets layer. It's a fully AIT owned TFTP library. So trivial file transfer protocol is pretty common. It's built into a lot of operating systems out there, but for the specifics of data load functions and to do things efficiently, we actually have our own library. It's 100% our source code, and it's primarily so that we can tune it and hone it to do data load operations as quickly as possible. Then the user application can access both of those libraries. To do just data load operations, the user application really only needs to use the 615A loader library, and the loader library uses TFTP. But in the diagram here, I just wanted to make it clear that the TFTP library API is exported. We deliver it with import libraries, documentation, samples, everything. So it's also possible to go directly to TFTP. That is useful in a lot of cases if you are doing things like testing a target device. So maybe you want to, rather than doing like a happy 615A upload operation, you want to sequence the file transfers and maybe even put some errors in some of the protocol files that are transferred between the data loader and the target. And so that's why we provide access to the TFTP library directly, specifically to support testing and verification type applications. The 615A library, has high-level functions for supporting the main 615A and 615A operations from the data loader side. So there's a find function, there's upload function, a function to initiate an information operation, and then also functions to initiate and execute operator-defined downloads and also media-defined downloads. And then the libraries are also configured, so there's a lot of timeouts, retry counts, IP addresses, etc., that need to be specified in order to make connections between the data loader and the target. And that's all done in an XML file. We provide a schema in the SDK. It's a very rigid and well-defined XML schema, so it's very intuitive, autocomplete, and all the easy things that you get with a well-defined schema if you're actually editing that XML in an editor like Visual Studio or XML Spy or some of the other XML tools out there. So I have at the top of the slide here, hopefully you're able to see it. It's a snippet of a very simple XML configuration file for the TFTP library and also for the ARINC615A library. So at the top, you see the LAN TFTP there. So within that element, you specify the TFTP client and the TFTP server. So in order to do a data load operation, a data loader has to be both a TFTP client and a TFTP server simultaneously in order to actually execute that operation. So in this configuration file, we're defining both the client and the server needed to do a data load connection to a target device. And you can see some of the information. This certainly isn't exhaustive. If you're interested after the presentation and send me a note, I can send you some more of these sample config files, and I can probably also provide the schema so you kind of get the all the information and all the available options that you can set for the different protocol layers that you define the configurations for. But in this one, we're setting, for instance, the range of UDP ports that you want to use. So you may want to be able to configure and restrict which UDP ports you're using on the local system to do file transfers. You would want to do this so you don't have collisions with other applications, or if you're doing multiple data load operations to multiple targets, you want to make sure that you're managing which ports each of those operations are occurring on. So that's why those are in there. So for each server and client, you can set ranges of ports that you want it to use. And then you can set things like the TFTP options, like the block size. So the size of the blocks that you chunk files into when you're transferring them, and also timeouts. So here we're setting an end of transfer timeout. There's 3 or 4 different timeouts that you can configure for the TFTP protocol also in the config here. Then below that, you actually have the configuration for the connection to the loadable target that you would load with this data loader. So to connect to a target, you want to know some identifying information like the target hardware ID in the middle there, also the position. So if it's a left, center, right, for example, if you have multiple instances. And then you would need to provide the data loader information like which IP address you're going to communicate with that specific target using. And then obviously for that target connection, you have to reference the TFTP client and server that you're using for communications with that. So that's what the client reference ID and the server reference ID is. So this is an example of what we're talking about with this XML file here. It's got both a section for configuring the TFTP library and the loader library. So the TFTP library up here, the loader library down here. Okay, if we take a little look at some pseudocode for TFTP client, I'm sorry, this is a TFTP server operation here. So the first thing you have to do when you're using the TFTP API is you have to initialize the API. So that's what the init is, basically opening up the library and access to the C API. Functions built in that you can read out the version and show that. So that's what we're doing here. Then you want to load that configuration file to the TFTP API. So this would actually be a specification of a path to that configuration file that we were looking at on the previous page. Then you have to open the server instance. So we can implement and operate simultaneously multiple servers on the same system. So you refer to the server by its ID. If I go back up, that ID is this ID that's referenced in the config file. So that's how you specify which one you're opening up, the open operation here, and then simple function to start the server once you've opened it up. Then you would basically sit in a loop or wait, and the server is now sitting there waiting to receive incoming connections and file transfer requests from a client. When you open the server, you're also able to provide pointers or references to two callback functions. So these are entry points in your application that the TFTP library will invoke when a request is received. So if a client contacts the server and says, I want to do a file put request, this the callback function that you register here will be invoked by the TFTP library. And then your application will be able to, in the return values and return parameters for that function, your application will be able to indicate if it wants to accept or not that application. And it can also return information like where to put the file or where to get the file that's being requested to read or write. Then there's also a callback function that you can register when you open the server that will get invoked by the library every time a file transfer operation completes. So if you started up the server here and a TFTP client asks to do a write request to write a file, first this function in your application would get invoked. If you accepted it, then that operation would execute, and when the file transfer was complete, then the transfer complete callback function in your application would be called, and the library would indicate in that callback if the file transfer succeeded or failed. So if the file was either uploaded or downloaded, depending on which type of operation it was, and if it failed or succeeded. You can also just asynchronously read the status of the server. So there's just a function in the API that you can say, tell me if the server is currently active and if it's transferring a file and how many blocks of that file has it transferred, etc. So that's what this is showing here. Typically you want to you start the server, and then you want to, when you're shutting down, you want to read this status to make sure that there's no ongoing file transfers. Make sure all the transfers that may be in progress complete before you then call the option or the API function to stop the server and then close the API and shut it down. So pretty straightforward, pretty simple API on the server. On the client side for TFTP, again, you have the same init function. You also have to configure the library with the XML file. If you remember when we showed the snippet of the XML file, there's an element in there for specifying the configuration parameters of the clients. Then you have to open the client. Again, you refer to it by the ID, the unique ID that you give it in that XML file. Then you get a handle back to it that you use in subsequent functions. This example is an example of the case where the TFTP client is writing a file up to the server. So it's a file put. When you call that, you have to give the address of the server you want to communicate with. So this is the IP address. You want to give the file name that basically it's the path to the local file that you want to put to the server, and then you can specify the name you want the file to have when it's written on the server. So this allows you to have a file that's maybe named file1.hex that I can say this is the file I'm putting, but when I put it to the server, I want it to be called this file name. So this is the destination name of the file on the server. Once you call this function, the file put operation is started. It's a non-blocking function. So then you can read the status of the client in a loop until you see that the file transfer has completed. And then after that, you can close it down if it's just a single, a simple application like this where you're just doing a single file read or write. So after you use the get client status to see that the transfer is completed, you can then close the client and then close the library. So this could be an example of a really simple function that you create using the API to just say from a command line do a file put. There is also the ability when you do the put, you can just like with the server, you can asynchronously read the status of the client, but you can also in this example they're null, but you can also specify callback functions that give you information about when, or basically indicate from the library back to your application when the file put or file get is completed. And then there's also a callback function that gives you status. So it'll basically call back every time a block of the file is transferred, so that you could do something like show a rolling block count of how many blocks or how many bytes of the file have been transferred while the transfer is actually executing from your application. All right, next we'll look at the 615A data loader C API. So now we're up at the level where we're actually doing data loader operations. So just like TFTP, you have to initialize the API. You can get the versions out of it. You then have to configure the API by passing it in that XML file that we looked at several slides back. In this case, this function is going to ingest into the 615A API those 615 configuration settings in the 615 section. You then have to open a target connection. So if you remember back to the XML file, there was, you're basically specifying the connection, the IP address and the communication parameters, and the TFTP client and server that you're using to communicate with an individual target loadable device. So here you're actually opening and getting a handle to do operations on that connection to that target LRU, and you specify the ID to match the ID that's in that XML file when you do this. The target, for each target connection, you can also register callback functions. So give references to functions in your application that the 615A library will do to indicate events that are happening when a load operation is occurring. So what you basically do in this function when you open is, this is a bit field input, and you tell the library which events you want to be notified of, and then you provide the reference, the pointer to the function in your application that you want to be called when the events that you've enabled notifications on occur. So these can be things like notify me when an upload request comes in, or notify me when an error occurs, things like that. Then to start an upload operation, it's very simple. After you do all this, simple command, upload, you give as input the path to the loadable software part or the media that you want to load. And then, I'm sorry, I'm not remembering right now what the true false is. I think this is also a matter of enabling or disabling the events during the operation. So you can kind of enable them for the connection to the target, but then for each operation, you also have the option to turn them on and off. It's a non-blocking function, so this callback is going to get called back while this upload operation is executing, but then before you would actually shut down and stop the target connection, you would want to check the status. So you can do there's a target get status, so this is checking the status of the connection to that target, and it's going to indicate if there's operations ongoing. So typically at the end of an operation, we sit in a loop and we're checking that status until it goes to no op, and basically meaning it's sitting idle, and then you would shut down the library. So pretty straightforward. You load up a config file, start the operation, you can read some status, and you can register some callbacks to get notifications from the library as different events happen during the load operation. We have similar functions for download. For download, it's more you're saying the media path to where you want to put the files that are downloaded from the target. There's an information operation in 615A. Same thing, it's info op, and you're given the path to where you want all the information that the target sends back to be written into a file. So pretty straightforward, pretty easy, pretty compact to do basic operations, simple applications. The library's handling all the details of the protocol for you. Moving on to the target SDK. Showing the components of the target SDK over here. So just same architecture as the data loader SDK. You have the TFTP library and the TFTP API. It's the same library and the same API that's used on the data loader side. You then have the T615A or the target side library that's doing the target side 615A protocol and a C API to that. And your user application has access to both. You have the same configuration parameters, an XML file for the target library and the TFTP library. In this image, I'm showing that configuration data can be either in XML, or we also provide a compiling tool that you can use on a Windows host to compile that XML into a more compact format, into a hex file format. And that's primarily used for targets that are on implemented on embedded, really lightweight operating systems where you don't want all the heavy-duty code that you have to do to parse an XML file. So for the target, we can alternatively read in the configuration data in an Intel hex file format that's going to be much smaller and also much easier to process on an embedded system. And like I said, we provide tools to basically convert the XML config into this more compact format that you can use on the embedded targets. So that's why two file types are shown there. Let's see here. So again, this supports you develop applications that go in your user target LRUs. We handle all the protocol overhead, all the TFTP file transfers, all of the status information that needs to be provided back to the data loader during the load operations. The target API also provides events and notifications as the operation is ongoing. We'll dig into that in a couple slides a little bit more here. The target API also verifies all the load files when they're transferred. So we'll talk about it in a couple slides, but if you were at any of the previous webinars, we talk about ARINC615 media sets and how there are overhead files, like a header file embedded in it that include CRCs, file lengths, and different metadata about a loadable software part. So our target side library will read those 665 specific files in addition to the application specific binaries. And when we receive those on the target side, we do all the CRC checks, all the length checks, part number checks, etc. And we take care of all that verification that the transferred software still has integrity once it's received on the target. So that's really the value of what the library is doing here, is it's handling the protocol, and then with the protocol you have all of the overhead files that allow us to guarantee the integrity of the transferred software parts once they arrive at the target. Hopefully this is something that everybody can somewhat see. If you can't see it too well, hopefully you can see it better in the video after we post it. But what I've tried to do here is show, so on the right with the colored blocks in the flow chart, we are showing basically the flow of the protocol that's right out of the ARINC615A spec. And then on the left, it's the sequencing diagram of the target API, the C API. So what you see is, just like with the TFTP and the data loader API, you have to configure. So this is where you're passing in the XML configuration for the target side. So that's the first thing you have to call, the first function you have to call in your app within the target API. Once that's done, then you have to open the target that you're simulating to get it handled to that. Well, when you do that open call, you're registering some event handlers or some callback functions. So one of them is this op request handler, and then there's also a loadable software part handler. So, but once your target side gets to this point where it's configured and you've opened the target, it's basically sitting there like a server waiting for a request to come in. And that request comes in from the data loader. So basically we're showing this is where the target is up and active, and now it's sitting and waiting for an operation. So if we go over here to the protocol file, or I'm sorry, the protocol flow, the way an upload operation would start is the data loader would first do a read request of an LUI file, so a file with an LUI extension. So that is what would basically, when that occurred here, what you would get is you would get this event handler would get called back when the target receives LUI read request from a data loader. And so in that event handler, we're indicating to your application that a data loader is out there and it wants to do an upload operation. And so this invokes that function in your application and allows your application to then signal back to the library if it accepts that upload operation or not. So that's what would happen there. So then if it was accepted, then the target side would actually transfer that requested LUI to the data loader, indicating that it wanted to do the operation. The next thing that would happen, if you follow the flow here, is the target would have to start sending status, which we handle. I'm not showing it here, but the target, basically once you've accepted the operation and sent the LUI, the target side in our library will spin up a thread and start sending status to the data loader saying, we accept the operation and it's active on our side and we're waiting for the data loader to do the next step. The next step for the data loader is to send the LUR protocol file over to the target. This is the protocol file that contains the list of all the loadable software parts that the data loader wishes to upload during that upload operation. When that LUR is received on the target side, that would invoke the LSP callback function into your application. In that LSP callback, what the library is doing is it's providing the application with the list of the loadable software parts that the data loader is requesting to upload to the target, and that allows your application to inspect those software parts and then in its reply to the library or its return values of that callback function to indicate to the target library if it accepts the upload of the presented software part that the data loader provided. Then once that happens, basically the target library goes down into this flow down below. It's the file transfer phase. So what the target library is doing is it is spinning through the loadable software parts that were received in this LUR file, and it's requesting those software parts from the data loader one by one. And it's also, the target library is simultaneously continuing to send these status files until the operation's complete. Once the operation's complete, all the files are read by the target library from the data loader. It will check all the CRCs and file lengths and part numbers that were provided in the LUR file and in the header file for the software parts that was read. And if everything completes successfully, it will call the event handler indicating the event that the operation completed and it completed successfully. So on the application side, again, basically what you need to do to implement this is pretty simple. You have to load up the config file that you create in XML. You have to open the target. Then you sit in your callback functions and you wait for the library to tell you if a load operation has been requested. You can then decide based on the state of your LRU that you can inspect in your code inside the callback. You indicate to the 615A library if you want to receive that file or not, or that load operation or not. And then once the actual software parts are presented by the data loader, you also get the callback in your application and you indicate if you want those parts or not. And then for the parts that you want, the library takes care of all the transfer, all the checking, and then it indicates to you at the end of all that if it succeeded, and also provides the location of where the files are on the local target system. I kind of jumped through that here. I forgot I had these, sorry. All right, when we talk about configuring the target, it's a little bit more complex. So first of all, as you can see here, on the target side, every target actually has to simultaneously be a TFTP server and 2 TFTP clients. If you go back to the flow chart here, on the target side, you have to, while you're in a thread reading all of the files that are part of the load, you also have to simultaneously be putting files, status files, to the data loader. So that's the reason that you have to configure 2 clients. One client's used to transfer the actual load files, and the other one we call a status client. It's the client that's in a thread and periodically sends status back to the data loader as required by the protocol. And then you have to be a server also, because the server is basically the state that the target is sitting in when it's waiting for a data loader to connect to it. So every operation is kicked off by the data loader acting as a client and requesting to read an LUI file or one of the other protocol files from the target side. So you have to configure for every target you want to have active in the library. You have to configure 3 TFTP entities, 2 clients, and a server. Then you have to configure the loadable target. You have to, for each target, you have to tell it kind of its identity. So this is that identifying information that the data loader needs. So it's the target hardware ID, the manufacturer, there's a type code that you can set, and also the target position. Then what you can optionally do in the XML file is you can specify a list of loadable software parts that you want that target to just automatically accept. So if you remember in the flow of the functions, when the list of software parts is provided to the target in the LUR file by the data loader, you can have a callback function invoked in your application where your application can inspect the part numbers and the loadable software parts the data loader is asking to load. And it can, in your application code, make the decision if it wants to keep those parts or not. But we also provide the option to keep your application code more simple, where you can specify in the XML config which loadable software parts you want to receive. And if the part that comes in from the data loader has been specified in the config, rather than asking your application, the library will just handle that part as specified in this XML config. So what you can see is you can even, for each software part, specify in the config the path to where you want that part and the files that are part of that part to be placed on the target side. So the reason that we did this and that it's implemented this way, where you have the option to implement that in source code on your target side or in XML on the config side, is this allows the target side, the LRU application, to be much simpler and much more flexible. We have a lot of applications where what the user does is they actually, for every load operation, they load 2 software parts. The first software part is this XML file. So they load it up to the target, and it says where to put all of the files from the part that it's going to load subsequently in that load operation. So the idea is you do a load operation to load this XML, then it gets applied to the target, and then in the operation right after that, you do another upload, which is the actual loadable software that you want to load. And so by this way, you have ultimate control from the data loader side without having to really change any code in your target. You can just change the XML file, have it paired up with your actual loadable software, and load this before you load your actual loadable software. Then basically you have ultimate flexibility on reconfiguring where you put loadable software in your target without having to go change the source code or the software on your loadable target. All right, jump down to the media set builder. So as we've described in some of the previous webinars and talked about, ARINC615 is in the family of ARINC615A specs. It's referenced by 615A. All 615A data loaders only accept software parts that are configured into ARINC665 LSAPs or LSPs. 665 also allows you to combine multiple LSPs or LSAPs into a set of LSAPs called a media set. the media sets can, if you're doing physical media, they actually still distributing them on physical media, they allow the media set to span multiple physical devices. So there's specific fields in there where you can encode and say this is disk 1 or CD 1 of 5, etc. So it allows to have a multi-physical media set. It's not used too much anymore, really at all, but it is because everything is distributed electronically, not on physical media. But it is possible and supported by the protocol. An LSP consists of a header file. That header file's format is defined in ARINC615. Really what that header file contains is the part number of the loadable software part, and then a digest, which is basically the name of each of the files that part consists of. And for each of those files, component files, it has the file length, the part number of the file, and then also a CRC that's calculated over that file. You can also optionally embed several support files and other kind of extraneous files that aren't the actual executable into that LSAP. And so there's basically accommodations in the header file format to specify if a file is actually part of the software part or if it's a support file or a data file that goes along with the actual binary software. So if you look at what a loadable software part would look like in a file folder, it would look something like this. So all these INI files would actually be the software part, and then this LUH file would what would be created by a 665 media creator, and it would basically contain the name of all these files, the lengths of them, and the CRC of them that was calculated over these when this header file was created. Like I said, this really doesn't come into play too much anymore, but you can take several of these LSAPs that are a header file with all the software parts. You can put them in folders next to each other, and then you can combine them into a media set part or a media set. That media set part is basically it's built up of two other ARINC615 specified files. One's a files.lum, which is again just a digest of where all the files are in the subfolders. So for every file name in the subfolders, it gives you the location of that file, the length, and a checksum over that file. And then the loads.lum is basically a manifest of all the loadable software parts. So it gives you the name of all the header files that will be down in each one of these LSPs, and also the CRC and the absolute path to where that header file is in the folders below the root folder where the loads.lum sits. What we provide a media builder tool. It sits right here kind of in the flow. So if you think of kind of the progression from the application software that you would run to upload to your target LRU, you would have the source code in whatever form that's in. You'd compile it into your binary, executable, or libraries. Then those are what go into our media builder and are packaged into an ARINC615 LSP, which is basically the header file, or a media set part if you have multiple of the LSPs combined into one entity, basically. With our media set builder, we provide both a UI and a command line to that. This is a screenshot of the UI. So you can see it's pretty simple. You can add header files to it, and then for each header file, you can add all of your basically your binary files that are your software part. For each one of those, you can say if they're a data file, a support file, or the actual software files. You can give a part number for each one. Depending on the version of ARINC615 you use, you can specify the checksum type or the CRC type that you calculate over that file. For ARINC615, beyond the -2 variant of the protocol, so -3 and later, there's multiple options for the check type that you can use, or the CRC you can calculate over each of the data files. You can also give a part number for each of the data files of your software part. You can input a part number for the whole software part. And then from here, you would basically save this out, and that would generate that header file. And then you can also save If you have multiple header files in here, you can use the LUM button to save it out as a media set. So this would generate the files.lum and the loads.lum and put all of the software parts or header files and their associated constituent files into a media set. So that's really briefly what the UI looks like. The media set builder also comes with a command line. This is what is most commonly used. Most commonly you have this process and the media set builder command line is used, so you can have creating the 665 LSP part of your whole kind of like automated scripted build chain. So you'd compile it, and then, you know, in the make file or the build file or the build scripts, you would then also invoke the command line media set builder to take those binaries and package them up into a software part. The way the command line builder works is you invoke it. We have an XML file that sits next to it that basically specifies all of this information, like the path to the constituent files, what type of file it is, the part number for that file, and the check type you want to use. So all that information you're putting in the UI, you can also put into a well-formed XML file that we also provide the schema for. And then that's one of the arguments, is the path to that you pull into the command line when you're building a media set or a loadable software part. And then what that's going to spit out is it's going to spit out, you know, basically the header file that's covering all the software parts, or I'm sorry, all the files that are part of your software part. That's kind of the end of the slides here. I was going to show very quickly just to give you an idea. I'm going to show, first I will show you from the command line here. I'm going to operate the media set builder. So let me also pop open a file browser and get to that. Second. Okay, so on the command line, I'm down in this folder. What I'm going to do is invoke this media set builder batch file. I'll show you what's inside of that. So that batch file, what it's doing is it's invoking the media set builder. It's telling it the path to the XML file, and then the path to the LSP, the loadable software part that it wants to build based on that XML file that's input. It's building two LSPs. So there's one XML file, LSP1, and it's putting it in the LSP1 subfolder. And then there's another XML file specifying how to build LSP2, and it's putting it in the LSP2 folder. And then for a third time, we're invoking the media set builder with a media set spec, which is an XML file. And we're telling it the root folder that it sits in to go look for these two software parts and build those into the media set. So if you look at it, here would be the subfolder with LSP1, and if I opened up the XML file that's specifying LSP1, you can see I'm giving it the name of the header file I'm going to generate, the part number for that loadable software part. We didn't talk about this, but for each software part, you give one or more target hardware IDs. So this target hardware ID is one of those identification parameters that you put into your target when you're configuring it. And so in the media set or the LSP builder, you're specifying the target hardware IDs of the targets that this software should be loadable to. So what this allows the data loader to do is when you give a software part to the data loader, it checks the target hardware IDs embedded in it, and it won't let you load this part to a target that doesn't have a matching target hardware ID. So that's what that section is. And then you have the data files where you specify each data file and the part number that you want to use for each data file. And then you could optionally, if you just weren't using the default CRCs, in another element here, you could say the type of CRC. So I think by default they're CRC 16s and 32s, CRC 32s. And then with the later versions of 665, you can do things like SHA-1 and more, I guess, elaborate, more safe CRCs, more resilient CRC methods you can use. So this is basically what these LSP config XMLs look like. So I'm going to open up the MSP. So that's for each of the LSPs, and then if you want to look at the MSP, so here you're saying the part number of the media set part you want to create, and then you have the LUH that you want to include in this for each one of these. So here I specify the LUH file that's down in the LSP1 subfolder, and then the LUH that's down in the LSP2. The media set part, you can also set the target hardware IDs that media set part should be used with, so that you see those again in here. You can set those in here. So then from the command line, it's pretty easy. We're calling the batch file that we were looking at here. So we're invoking this, building media set, or loadable software part 1, loadable software part 2, and then the media set part. And you get output like this from the media set builder. So first invocation, we're creating LSP1. It tells us that it was generated and where it's at. LSP2, it was generated and where it's at. And then the whole media set part, it was generated and where it's at. So this is the kind of output, say, if you put this into your build scripts or your build chain, that you would get from the media set builder. So that's the media set builder. I'll do a quick show and tell of some applications running from the target and the data loader SDK. So let's see here. I have the target running over on another system here. So I'm actually going to close the application and restart it. So with our target SDK, what we've actually done here is we've created a sample application that loads up a configuration file, and in that configuration file, it actually allows us to simulate multiple different types of LRUs. So the target SDK can present itself, an instance of that can present itself to a data loader actually as multiple target devices. In most cases, that's not done, but there are some cases where, for example, you may have like a subsystem where you have a gateway, say, that's a server or some kind of a processor that's running an operating system and has a network connection. But then downstream from that gateway, you may have other components of the avionics system that aren't accessible over Ethernet, that maybe are over a serial link or an ARINC429 link, but they actually are loadable. So you want your loadable target is actually a gateway that's going to receive the 615A loads, but then move that software down over a serial link to another LRU. And so what this allows you to do, because the target can basically appear like multiple targets, is you can make each one of those downstream nodes in your subsystem look like a 615A target back to the data loader, if you have a situation like that. So that's somewhat what I'm doing here. So in this application, I load up the configs, and then I give you a command line to open one of those. So I'm going to open this HNP FMS. So I'm simulating a Honeywell FMS system here, and that's at ID 5. My alignment on the printout's not too good there, but I'm going to open that one up. So now over on this target, which is at IP address 42, I have I'm simulating, or I'm running a target side that's looking like the Honeywell FMS. I'll come back over to the system I'm on right now, and I'm in a window with my data loader. The first thing I'll do is the data loader application. This is our data loader command line, which is just an encapsulation, a simple application that uses the data loader API that we walked through the pseudocode on. So here I'm going to use the data loader API from the command line to do a find operation to that address where I have that target running. So what I'm invoking here is I'm saying I'm doing invoking the data loader over Ethernet to IP address. The E is an Ethernet find to IP address 42, and then I'm going to wait 3 seconds. So the timeout is 3 seconds for that target to reply. So if I got it enabled over on the other side, I'll see that it replies there, it responded, and it identifies itself to me as the Honeywell FMS, the position that it's at, the name, the code, and all the target type information and its IP address. So I did that. I can also load it. So what a load operation would look like from the command line is, see if I can get this a little better. So you do the data loader. The -U means I'm doing an upload operation. The -C means I'm passing in the target config, or I'm sorry, the config for the connection to the target. I'm using the compact format here, the hex format, because I had one readily available. And then within that, I have to tell it which target, because in this config file, I can identify multiple target connections. So I'm identifying the target hardware ID of the target that I'm simulating. Then the S is the position, because I may have, say if it's an FMS, I may have an FMS right and left, but they would both have the same target hardware ID, so I have to say which one, the right or left. So in this case, it's the left. And then with the lowercase -l, I'm specifying the loadable software part that I'm going to load. So I'm giving the path to the header file for the 665 part that I'm going to load in this case. So if I execute this, you can see I get responses back. So this is, these printouts are basically coming within the callbacks, the status callbacks that we showed in the data loader library that you can get. So this is status that the target is providing back as it's transferring this software part over to the target. The status counter that you see counting, that is basically an increment or a counter that's in those LUS or status files that the target sends back to the data loader. And the way the protocol works is the target should increment that for every status file that it sends. So that's what you're seeing there, is a status file is received with status information in it that the operation's in progress. And the load ratio is the percentage complete. So you can see we're at about 80% complete right now. And you get the complete. So the operation completed successfully. So both of those examples that I showed you, the one running on the target side and then also the data loader from the command line, we provide the source code to those as a reference implementation with the target SDK and the data loader SDK respectively. So basically what I was demonstrating is I was running the applications that demonstrate the use of those APIs that you get along with the documentation and the SDK. So that brings us to the end here. Just reviewing, we covered the data loader SDK, its software API, and its configuration parameters. We did the target SDK with both its configuration parameters and its software API, and then we looked at the media builder and how to use it from the user interface and the command line. And when you get or purchase the 665 media builder, you get both. It comes with both the user interface and the command line version of it. That concludes the tutorial and the overview today on our SDK products for 615A.